So today we'll discuss some number theory problem. So knowledge-wise, I think number theory problem, we have all the knowledge needed, right? So if you have any certain part not that clear, such as you grab like an ordinary number theory books, some of them like events, IB, this one. This Roseanne, that's also good. So those are two books. And some people, if you prefer old classical, Hardy. So today we'll mainly just based on all the knowledge, and let's try to attempt solving some of those and then discuss how you reach those. So you have infinite positive term and negative term. And then this from any n you get complete relative set. Okay, so try to understand. If we have 1 to n, then definitely this one has satisfied the requirement. The only issue is it does not have a positive number, a negative number. And then you want to have infinite positive, infinite negative. If you subtract 1, subtract a large number, then you're going to get some term positive, some term negative. So let's think about, can we find the one that satisfies the requirement by shifting and then infinite? Think about this infinite hotel problem, etc. So probably with a little bit, if you keep your mind open and you realize this type of thing satisfy the requirement, but then this is not approved. It's just for you to to appreciate how to find examples, and then next we need to prove it. So to prove it, you have to show this each number show up exactly once. And to show up exactly once, naturally, you can use proof by contradiction. And suppose you have AI AJ, then from here, if we simply mod J, then you have two terms. They are identical. So we cannot have two terms that are equal. And next, you need to show every number occurred. To show up every number occurred, what you can do, try to show a specific number. Let's start with 0. So we need to show 0 occurred. Naturally, we also use proof by contradiction. And if it does not occur, then suppose we have A1 greater than 0. We can do that, right? Because otherwise you just multiply -1 on each term. So with this one, because you're going to have positive term, negative term, so there will be some term that will change from A1 to a certain term, and then you will encounter your first negative term. And then here we notice they need to be distinct. So now if we just simply calculate this, the difference between two terms, xi equal ai minus aj, I from 1 all the way to k minus 1. All this should be positive, and then they should be distinct, right? So if this one distinct, then from here, we know this, you have k minus 1 number, all positive, and they're all distinct. So there should be at least one that is not, it's greater or equal k. So there must exist, let's say, xj greater or equal k. Okay, if that's the case, then think about what happened from here. Anyone figure out from here? You look at the first xj term. With that one, what can be concluded? Will equal ak mod xj. So that shows you you're going to have those two that are earlier. We already know that all the terms are distinct. Now you have two that's equal, so that's contradiction. 0 need to occur. And next, how do we show this? Any number should occur. And for this one, you can just think, if we subtract, if we want to prove for any m, this one occur, then you could just subtract every term by m. With what we proved earlier, the new sequence should have 0. That means the old sequence should have m, and then this one's done. Okay, so next we need to here this. If we want to, since we already think about this problem, and in the competition, you don't need to really do this next step. But while you practice, you could think about how do we find out all this such kind of sequence. Earlier, we mentioned this one satisfied. So you can see it's not difficult, even though this is IMO problem. This is IMO number 2, I think. This is IMO number 2. How do we find out all of this? So you see, earlier we did this alternate, but if you check, can you modify this one? And if you check it, that's, you could just it's kind of like an insert. That's a negative sequence into a positive sequence. You keep the way it is. So like down here, we can do the -1, -4, -2, -3, 5, 6, etc. And with this one, if you check it, this one, I think here, this -3 should goes back. -3. This one also valid. So if we think about this one, you could, with how we generate all the sequence. First of all, you could make the first term equal to 0, right, by simply like subtract a common number. So that means after you've done that, you can add any certain number to this new sequence. And then there's a next term. Next term, you could make this to positive. Otherwise, you can just simply multiply a -1. And in order to make the first two satisfy the requirement, so must be 0, 1. And then next, think about what is the first negative term. First negative term, you can see definitely need to be -1. Otherwise, you can see there will be some contradictions, right? Earlier, you won't be able to fit. And so with this way, we can see it's just all you do is just insert this sequence and from the 0, the non-negative number sequence, and then you can insert a negative term at the right place. Yeah. For that one, you if you think carefully, you can also try to think like when is the first time you could put in a negative, right? And then like if we have, say, suppose k plus h terms, the first k plus h term. So out of this one, you have k minus 1 positive, and you have h negative. And then we know that means you already have 0, 1, 2, all the way to k minus 1. And then you have -1, -2, minus h. And then what is the next term you can put in? The next term we can put in. Clearly, you need to put in either k or minus h plus 1. Otherwise, you can there will be contradiction. If it not, suppose we have this k plus h plus 1 greater or equal k plus 1. Let's see what happened. How do you want to find that contradiction? You could let n equal this number plus h. And if you mod n, you'll find that negative h equal a k plus a plus 1 mod n. So that's contradiction. Similarly, if you have a k plus h plus 1 less equal minus h plus 2. You can also choose 1. And at this moment, what we need to choose, same thing, you want to show those will have contradiction. So you can choose at k minus 1. And in that way, the k minus 1 and this new a term, the congruent. So from here, this shows you can have any sequence that just puts it, write them in order, and then after that one, you could switch the sign, you could add any certain number, and then it's always valid. So it's just, while you do a problem, and then you just try to extend a little bit. Next, this one is AMO or JMO problem, I forgot. But anyway, just find n, and then find all n. Find all n. That's all its factors except 1. In a circle, adjacent term, adjacent pair, right a prime. Right. Understand this one, right? And again, you could this one that's down here, just to make it all composite number. Otherwise, if it's just a prime number, not a circle. So that's a minor thing. That's in the real problem. It's an AMC, AME, JMO, AMO problem. They are very rigorous. So minor thing, not an issue. So for this one, what you can do, you could start from a few smaller cases. Let's think about 6, right? That's as small as we can go. 6, can we put them in order? Definitely no. Right, 2, 3, 6. Okay. So no matter what, it's not possible. And this one, so just by trying this one, you already get some hint. This one, you must have more than 2 prime factors, right? If 1 factor, very easy to show this not possible. And more than 2 prime factors, how do we arrange them? Let's say n equal PQR, PQR are prime. And this one, what shall we do with this? I think it's what can we do with this one? So with this one, let's see, since we want them to be adjacent, down here I miss one, not right a prime. This is 2005 AMO 1. I missed that. PQR. So what we can do from here, then PQ, then Q, go to QR, and the R, then PR. And then next down here, there's a P you could put in either places, that's fine. So this gave us the 3 factors, and without exponent, and we can arrange them. So how do we do for the general term? General case, n equal P1 to the, let's say, alpha 1, P2 to alpha 2, Pt to the alpha t power. And how should we do this one? We're thinking about maybe try to find a way that's from number of prime factors. See how many we can do. And with 2 prime factors, we definitely see that's not possible. And 3 prime factors, you also have cases, let's say n equal to p squared q. And how do we arrange this one? So let's, for this, probably better for us to first deal with anything that has P. And we start with PQ. You play it PQ, and then think out PQ, what next you can put in? That's P or P squared. If you reverse order, that should be also fine. And then P squared Q. Okay. And now with this one, on the right side, you have Q. And that's pretty easy to put in Q. Start. Right. And so this for simple problem give us some hint. How do we do the larger one? And what we can do is trying to, yeah. At this moment, when you write it, down here is the time for you to first on scratch paper, you figure out the way how you construct them. And then if that construction is clear, that means you could already express, let's say, the like at any position that's equal to one number, and then that expression is easy and also pretty easy for other people to follow from your reasoning. You could directly explain your construction. And if it's a little confusing, like I don't know how many of you did BAMO, and in the BAMO text, and I read some student solution, and intuitively they are correct, but then this, when they write the solution, it's not that clear. So for this one, you have to use some of those common technique, like from here. For our problem, probably you want to use a mathematical induction to show this is doable. And then you might need to use some graph, or earlier what we did, the proof by contradiction, that kind of thing, to demonstrate, to let the graders easily follow your approach, right? Because you understand that when you take this JMO, AMO test, everyone just, I mean, you're suppose you turn in 5, 6 solutions, and they will be graded by different people. So they don't have like a general idea how well you do this problem. They don't know you, and you're supposed to, I think, I forgot whether you hide your name or not. But anyway, you need to make sure that your solution give people a good impression, and then they have confidence in you that you indeed solve the problem, right? So down here, like the way I wrote it right now, it's not going to get full credit. If this is mainly just a motivation. And if I solve this one, I have to figure out on scratch paper, and then I will clearly write my notes. And then I don't want to make my proof or the essay part, each paragraph, you don't want to make it too long. You prefer to write them in sentence, and each sentence in different line. So make it easier for other people to follow how your idea progress. And so like down here, this one, let's think about it with more. How do we show we could put in? So earlier simple cases we already demonstrated, and now suppose we calculate the total number of prime factor. That means the prime factors, it's like down here, this one. You think this is, you have 2 prime number P, 1 prime number Q. And when it's 3, we already proved it, right? So M is total prime factor, total number of prime factor. That's duplicate. So we already showed this M equals 3, that's okay. Equal 1 or 2, not going to have solution. Then you try to show that how you can do more. Suppose since you always lose nothing by using strong induction. So at least in your reasoning, you could think, oh, strong induction. So the number factors, yes, let's say this S. S is a number factor. When this one is all correct, now this one S. Now I want to show that X equal M plus 1. We can also do that. So how do we do that? This one, from the prime factorization, you could think alpha 1 less equal alpha 2 less equal alpha t. And then that is B equal from the second prime factor alpha 2 pt alpha t. For this one, that clearly fall in our induction step. So this part can be done. And then this one clearly it should have it should have more than 3 greater equal 3 prime factors. Okay, so once this is done, we arrange them in a circle. And how do we put in that all those related with P1? How do we do that one? Good. What we can do, you see that P1, when you have P1, we introduce a new prime factor, then that one, it just has a correspondent with existing one, right? So like if we have if we have AI is a factor, then P1 AI also a factor. So those one has a one-to-one correspondent, and then so is P1 square of I, etc. And for this, we could simply just do originally, suppose that with this B, you form a circle, you can just cut those two, cut the circle anywhere. And then the 2 and 1, that's C and D. We know C and D, their GCF greater than 1. And to put in this prime factor P1, you could just simply add P1C here, P1D here. So it's kind of like a symmetric. And then that's P1 square, that part, you could just add the adjacent one. And it's very easy to show this left side, they have prime factor between any adjacent one, they have at least a prime factor P1. And right side already done. And this problem just done, right? Pretty easy to progress if you use the right approach. So like at the JMO, AMO, lots of time is this kind of thing. And at first, of course, this one is definitely easy, first problem. But don't expect like you treat the same way with the AMC or AME. Look at the problem and then you know what's the theorem related. You just try to get a feel of that problem and try to come up with some maybe even partial solutions, and then see which part need to be improved, like why some parts of the solution not working, and then you change accordingly. And then this will be done. And next, give you a one problem. It's just showing you prove this one. Probably lots of you already know, think this is already a fact. So that's for any k, it exists n such that 2 to the n last k digit have at least half equal 9. So how do we do this one? At least half equal 9. So you're thinking about in what scenario you're going to get at least half 9. So it must be k digits. So 10 to the kth power. 10 to the kth power, you subtract a smaller number. And then you get the leading numbers all equal to 1. So subtract a small number. And how does this relate with 2 to the nth power? So what you need to think, 2 to the, okay, 2 to the kth power. So here you think, if we let the 2 to kth power equal a smaller number mod 10, 2 to the nth power, right? So if 2 to the nth power, this equal a smaller number, let's say negative a mod, then this a, let's say, small. And then we know this one definitely it's should be, you should have at least half of digit equal to 9. And how do we show this exists? And what this number need to choose? 10 to the kth power. So we know at least 2 to the kth power divides a. And let's think about it. If we do this one, can we just choose this a equal to the kth power? And if we do that one, you will see this equal negative 2 to the kth power mod 10 to the kth power. This one equivalent to 2 to the n minus k power equal negative 1 mod 5 to the kth power. And we just need to show this definitely exists. And how do we do that one? Right. And then let's say for people who are experienced in number theory, probably you already know this is, you could treat this one as a known fact, but in its YEA AMO, you don't want to use this any conclusion you learn from a problem or not well-known theorem, and then you try to refer that one, because most of the graders, I think, will be graduate student, and they have their own concentrations and must have been a while. Even though you can count on them to know most of them, but if you use a pretty obscure theorem, they might not follow, and then they might think, they might try to pick up some part they think is not rigorous, deduct point. if you are not lucky, not fall in the cutoff, because in this JMO AMO grading, they will only really care about the top performing student, right? So maybe let's say MOP, they select top 50. I think they probably gave some cushion and re-examine the top, most top 100, most likely 70, 80. And if you scores, because of the grader misgraded or do anything that fell off that cutoff, you will lose your chance, right? That definitely happened. I mean, it happened to me before, but at that time, it's just lucky. It's just still quite personal. Like our province teacher know me, and then they know I should do well. So like they look at my solution, regrade it. So that put me from, like, initially at that time I was, I think that's number 5 or number 6, somewhere around that. But then after regraded, they put me in number 2. So that's making me eligible for this, that's like Chinese mob thing. I mean, I have a chance to go there, but if I original one, maybe I will just miss the cutoff. So, but here, when you grade, you don't have that portfolio. So if you have a shot at the mob, or you want to do well, at least you want to put yourself in that category, like a female student, 12. So probably you want to put yourself in the top 20-ish. So from here, if we want to show this thing exists, right? So they're just saying, this one just showing us this one, even though we know this is definitely true, but then you also need to prove this. Of course, for this one, you could just do torsion 5K, and then that tells you this one torsion 5K equal 4 times 5K minus 1. And then use this Euler theorem, and A to the torsion equal 1 mod m. And then from here, you use the primitive root and try to figure out the smallest possible. Indeed, is this number. And that way, this can be done. That sort of fine detail, I think you already know. We will not waste too much of your time. Right, so that gave you a simple one. Next, let's do a little bit and this one is, suppose I gave you a positive integer m, a, b, and a and b, this a and b right here prime, and a is a proper subset of positive integer n. So that stuff like this, any n, you will have either an belong to A or bn belong to A. Okay, so for all set A, satisfy this, find minimum of A intersect 1, 2, all the way to m. I don't know if you understand this problem, right? That's m and AB are given. They are positive integer, A and B relative prime. And then you have a subset of positive integer set n. So that's any n, you have an or bn belong to A. And then ask you to find out the minimum of this down here. A is not empty set. So what we do with this one, see, at first probably you don't really get a sense of this, and this one, the answer, if you think a 0, 1, or 2, probably will be a little on the easier side. That's not the solution here. So we try to just, as usual, if you have something, you just try to put in some concrete cases, try to start get a feel of it, and start from the really simplest, A be equal to 1. Okay. So now with this one, A is what? A needs just equal to the integer n. So in that case, this one, this answer down here will be M. Right. And then next, what do you think? A and B. A and B, they're not all equal to 1. Suppose we just do A greater than B, greater or equal 1. Let's first think, does this kind of set exist? Does A exist? Definitely. You can see at least you could choose A to be a positive integer set n. Right, so this definitely exists, and then we just want to make that intersection as small as possible. And so that tells you, because we just want an and bn, either an or bn in this one. They could both be in this, that's okay. And so that's, if you have number that's not a multiple A or not multiple B, then you can safely remove them. And that definitely will help reduce this cardinality of the intersection set. So that means here we can easily, this is any x, A, x, this A divide x or B divide x. Okay. So next, let's think about it. The all multiple of this. And all the numbers are multiple A or multiple B. And if you think about a number, multiple B, like say called B times C, and then C is not a multiple of A, what we can do with that one? We could easily remove this BC because we want to make the intersection with smaller number as small as possible. So you could easily change this BC to AC. Right. So with this one, you see this still satisfy the outer requirement, and then it will contribute to reduce the cardinality. And now with this one, you can see this tells you this, since we can remove anything to a multiple A, you could assume all the numbers, it's a multiple A. And next, let's think about what else we can help to reduce that number. Let's think about if we have A squared C, and then of course, and this one does not divide C. Well, we can change this. Do we need to keep this one? Can you follow this one? Do we need this A squared C? We don't. Because if you think about it, if we have any BC, then B squared C does not belong to A. So that means A times BC must belong to A. And if you remove the A squared C, there's a multiple of BC still exist. So we can safely remove this A squared C type. With this one, more generally, you can see this A to the 2k power C, not needed. Right. Can you follow this, why we could remove it? Down here. See, this way I should be more. If this one not here A, then this not here A. So that tells you this plus 1 BC must in A. Not in A. This one not in A. So indicate that's a contradiction to this outer requirement. So this type thing must in A. So that tells you 2k plus 1 times C times A, not in A. So in A, those are all have odd power. So this A just equal to odd power of A times some constant. So once you figure out this one, then how many elements in this? That's pretty easy. You're just using this PIE to calculate. Suppose like from 1 to m, and this k is the largest, so ak less equal m. Then you have m over ak of those that are multiple of ak, and then the total number for this one will be this m over ak time -1 to the k plus 1 power, k from 1 to infinite. So it's just this number. So this is just, again, just try to go from the small cases and then figure out what is the solution. Okay. Next. Suppose choose n distinct fraction from 0 to 1 and prove sum of denominator greater equal 1/3 n to the 3/2 power. Okay, so this is an estimation problem. And this one, the more important thing is not like the coefficient, because quite likely that you will not be asked to calculate the exact, the really tight bound, and that this one, the coefficient, normally it should be really easy to adjust, to improve, but this exponent is the main thing, right? So when we do this one, normally this n should be really large number. The smaller numbers, not that meaningful. Right, so the sum of this is n to the 3.5 power. So that means average is about divided by n, so square root n. And think about this. The smaller number, so this average square root n, is it true or not? We are not that clear. But then you can easily see, because when we calculate average, the smaller number is not that important unless you have quite a lot of them. And use the bigger number. The bigger number is, you don't want to be too many. Okay, so let's think about it. How many we have? And easy to see for this, if a denominator, let's say B, M over S over T. I should use P over Q. That's P over Q. So those Q will be either greater or equal T, or let's say greater than T. We want the equal side, or less equal T. And then for this less equal T, you have how many fractions maximum? Even if they're all distinct from each other, this less equal T time T minus 1, right? Because starting from 2, you have 1 fraction, 3, you have 2, etc. So this one is about T squared. Right. And so that's tells you this, the T, and here this T should not be greater than square root n. Otherwise, earlier, those less than T, you only have T squared of them. And if it's greater or equal square root n, then the total sum will already greater than n to the 3/2 power. Okay, so this is about half T squared. So this will be about n minus half T squared, roughly. And how do we calculate there? We calculate this one. So we just choose the T equals square root n. And then you calculate the sum of those. The sum of those will equal to greater than what? Right, this bigger one, and time n minus half T squared, so n minus 1/2 n. So this gives you n to 3/2 power. Right. So this just demonstrated if we just split those number, and then this, we try to put them in the two group, and the cutoff part is square root n. Right, and then this, for the smaller number, when you calculate it, you will see that's their contribution for the total sum, because here we calculate 1/2, and they try to prove this one. It's 1/3, right? So we can see that's again proved. This, in this type of estimate problem, you only need to calculate the the order of those, not this exactly number. Right, so yeah, so from this one, we understand the key thing is because the smaller fractions, you cannot have too many of them, right? So at most half t squared. And so that's why when you choose a t equals square root n, you have at least half of them. It's the denominator greater than t. And we use this method, we can already show this. You get a better one. Plus those half t square of smaller one that will only improve your lower bound. So this problem that's done. So this let me give you one more problem. This USAJMO problem, USAJMO number 6. And this I think it's 2005, number 6. I know. So this is ask you for give you a number and number m or the integer. Sm indicates the sum of digit, and then fn is such kind of a number. Okay, equal fn. Let's satisfy this condition. Any maybe like just me copy it over. And my notes help me, but it's this one. I cannot. So this one, definitely it's a little harder than the earlier one. And it's still an estimation problem. So you first look at the right side. And that means you need to construct a set of satisfy this requirement. So that's it has an element, and then you have the sum of those digits equal, and then you want this digit sum to be as small as possible. So less than log n time a constant. So there's a sum digit. Sum digit is, you want to show this in the order of log n. So let's think about we wanted the digit sum is all same. And then you notice in a simple smaller cases like those 9, 18, 27, etc., all the way to 81, 90, the digit sum is 9. But then this one, you only have 10 of this. And so do not give up so quickly. And what's the next number? How do you think about the next number? Yeah. Their number digit sum should equal. And then if you add any 2 or more, they should also equal. We did this sum digit equal to 9. The next thing is sum digit equal to 18. So like 99 times 2. Right? And then let's think about, we could improve this one to what? 99 times 100. And then with this one, now you have 100 numbers satisfy this requirement. So follow this same idea. Then because here we are dealing with this log base 10. So think about those 9 seem to be pretty reasonable, right? So if you thought about this one, the next thing is try to think those one, all those number 10 to the t power minus 1. This time some constant, and then you can see the digit sum for this one should just equal to 9 times t. And then you want those, there's a digit sum small. So what t you should choose? We need to have n of those. So you can just choose this 10 to the t, greater or equal the sum of first n number. And with this one, you at least at this moment should be enough. Okay, you think you find out the sequence, and then you solve most of this, and then of course really prove it. You have to polish your solution, etc., because the time limit. Not going to the detail here, but welcome you to take a look at this 2005 USAJMO number 6 and try to figure out. You can see this. The starting, it's not that difficult, and here's American competition. Like, they don't want to make you have to know certain kind of technique or certain knowledge. in order to proceed. They gave you a pretty open starting point. And if you think of the right approach, you could easily proceed. And so have a look at the problem and then try to figure out what is what the exam writer wants you to do, right? So if you follow that one, then likely when your paper is graded, and they are more likely to find the common part from your solution, between your solution and the official solution, and then you're more likely to gain higher points. And I've seen students when they obtain their solutions, not this solution, I don't have access to that one, but like I've seen some of those when they apply for other type of program, the solution, I've seen some of them, and they solve it, but then they didn't really think in the term of the exam writers, either write it too detailed or write it too terse, and either way it's not that good. So it's better to write them in a clear fashion, to figure out what they want you to write, and then go from here. And that probably also can lead you to the final solution quicker. All right, thank you. So here, I think I will stop here.